Okay, so with that, he'll be speaking today on deep learning framework for designing graph algorithms.
Okay, thanks for the invitation, and folks, thanks for the introduction. And what I'm going to talk about today is going to be deep learning over graph, and also using deep learning for designing algorithms to solve graph problems. So you might be familiar with deep learning for images, right? Convolution neural net for images, and then maybe deep learning for sequences, so like a recurrent neural net for sequences. But what I'm going to talk about today is more like a deep learning for graphs where nodes are connected with edges, and each node may have a different number of neighbors. You want to do some learning on this type of thing. And the key idea I'm going to tell you is also a new type of deep learning architecture, which is going to learn some kind of a propagation operator over the graph, and then tailor for different applications. Okay, so what happened in real world is you encounter this graph kind of data very often. It's kind of an abstract language for describing many different problems. For instance, you might have a social network like this, and each one is node maybe people, and they're connected to each other in a very complicated way. So and the edge may be actually temporal as well. So at different point in time, you have different friends, and it's evolving over time. It's a very complex kind of system evolving over time. You might want to build some model for making predictions. The simplest example maybe you want to predict if there's a tweet happening in the social network, how fast it's going to spread. In 1 month, how many people it's going to reach. Okay. So actually, there are other kind of prediction problem over the network as well. For instance, if you want to make a recommendation based on people's purchasing of particular products, essentially this kind of purchasing relationship is happening all the time, it's evolving all the time. You also want to learn some kind of feature for maybe each user or item, making some prediction. So for all these type of problems, you might also encounter some kind of cybersecurity problem. You want to detect some virus and fraud, and then there's even something related to healthcare. You have network structure. You want to actually design some algorithms either to extract features from this type of data, which involves networks, or you want to design an algorithm to work with this type of data, and then to be able to obtain some results. So typically, when you try to design some algorithm for a network kind of data, you have to first think about how do you actually describe this graph structure. It's not like a typical image or vectorial data. The data already comes in numbers, right? It's like a fixed dimensional vector for each one of its data point, and you can either use fully connected neural net or the fixed size image. You just use a fixed size convolution neural nets on top of it. So in this case, you have to think about how do you represent this data. So you have to think about how do I take into account the neighbor? Maybe the neighbor of this particular node. Maybe there's also additional feature on the nodes, right? Maybe the age and the location, things like this. And then there may be information, very rich information on the edges. Maybe these edges are about a particular person purchasing a particular product. It might contain rich information like the satisfaction level of the user, the comments of the user to the particular purchasing experience, right? And then it can be very complicated information. How do you incorporate those information? So then you have to design how do you represent this type of data. Typically, you design this by hand, think very hard what's going to be useful. And then once you design this type of feature representation, then you are going to figure out a way or design a way to actually update this feature to arrive at the prediction you want. So let me give you 3 sets of more concrete applications, such that you have a better idea what kind of application I'm talking about, right? So the first thing is, I already mentioned, it's the prediction problem for the information diffusion. Suppose you have a social network, a piece of information spread. You get to observe the spread of information maybe in the first week. I want to predict for a month, what is going to be the expected number of spread. Or the second problem, in this case, the input is also going to be graph, but the graph is very different in nature. Yeah. The graph is going to be a molecule, and each one of these nodes in the graph is going to correspond to atom, and the edge is going to be some kind of chemical bonds. And then you have different color for the node corresponding to different type of atom, different type of chemical bonds, different type of edges. So what you want to do in this case, you want to take this graph as input, each individual molecule, and make a prediction about its effectiveness in terms of treating some disease, or if it is some kind of solar panel material, you want to make a prediction how effective it is for essentially converting sunlight to energy. So going beyond some science problems, you also have information processing problems, such as understanding a sentence, understanding especially the sentiment, the people's view on particular things based on some kind of structure imposed on the sentence. In this case, the structure imposed on the sentence is a parse tree. You can decompose a sentence into noun, verb, or something like this, okay? You want to actually take an entire structure of in this case, a tree, okay, special graph, as the input, make a prediction. So we have also tried to use graph to represent computer codes, right? So in a computer program, there are many different functions. They call each other and form a very complicated graph structure. And then there may be a malicious code. There may be normal code. You want to make a prediction whether this particular code is malicious or not. Then you want to actually also want to classify this graph structure based on both the connectivity and also some information on this node. So let me show you one application where it involves a large amount of data. We got this data from Harvard Clean Energy project. So they have done DFT computation for 2.3 million organic molecules. Yeah, all these molecules is trying to target towards high power conversion efficiency from sunlight to energy. So they have done this DFT calculation for many years, okay, to collect this 2.3 million data set. Each one of these molecules is attached with a number between 0 to 12 about the power conversion efficiency. So the goal here, the learning goal here is to take these data set. Each one, the input is going to be molecule, output is going to be this number, and build a regression model, okay? So first you have to think about how do I represent these molecules, right? So the traditional way of doing it is designing some feature. So this is this simplest feature you can design is called a bag of substructures. Essentially, you're going to decompose this bigger molecule into some substructures. In this case, I'm looking at a very simple substructure like trees rooted at a particular node. For instance, I can count how many occurrences of this type of substructure in a particular molecule. So it is a center of the blue atom and then connected to two gray atoms. Or I may look at this type of structure, center node is kind of a yellow atom. So here I can find one occurrences in the first molecule and then two occurrences in the second molecule. So the corresponding feature dimension is going to be 2 for this case and 1 for that case. You can imagine I can enumerate more and more complicated substructures and count occurrences of these substructures in the corresponding molecule. And each one of these substructure is going to correspond to one of these feature dimensions. So in the end, I can actually keep looking at the more and more complicated substructure. If I look at a center node and the neighbor of the node, neighbor of the node, and enumerate the structure up to degree of 6 separation, then I can get easily 1 billion kind of substructures. And I can use a 1 billion dimensional feature vector to represent a small molecule like this, although it's very sparse, okay? So you find that you actually need this 1 billion dimensional feature vector to get state-of-the-art performance. Okay? You need the 1 billion. So your model, you have to first enumerate this feature, and then the model is very, very complex at next one. So of course, people have designed a clever algorithm to represent this graph. It's actually iterative algorithm to enumerate these substructures and counting these substructures and compress along the way. Okay, how do they do that? So essentially, the way they do it is it's based on some graph isomorphism check algorithm. This algorithm called Weisfeller-Lemon algorithm originated from computer science. So essentially what you do is, for instance, for this particular molecule, I'm going to represent each node as some vector, okay? HI, for instance. And then I will going to initiate this HI with just the node information itself, the type of atom, for instance. I'm going to hash, you can think about some kind of dimensionality reduction you designed beforehand. Hash it, okay? So you have some vector representation. Then I'm going to update this representation using iterative algorithm, okay? This iterative algorithm is going to essentially, for instance, if I want to update the embedding for this center node here, I will ask the neighbor of this particular node to send in the information, send in their vector representation, and do some aggregation. The simplest one is, because it's vector, I can just sum them together. And then once I finish that, I will incorporate somehow the information in that particular node and rehash it again, transform it again. So again, in this case, this hash or dimensionality reduction here is typically hand designed, okay? And then once you finish this iteration for each one is node, and down in for t times, you will converge, maybe you obtain some vector for each one is node. Then you aggregate them. Aggregate all these vectors, call this single vector as a descriptor for the entire molecule. Yeah? If you do that, you can actually reduce the number of parameters. You can get a denser kind of representation for each molecule. Maybe you reduce the number of parameter by 10 times. And then you can still obtain about the same predictive accuracy for this problem. You can, of course, compress it even more. So the more you compress, the more you lose in terms of predictive accuracy. But what deep learning can do, this learned propagation operator I'm going to tell you about, is able to reduce the descriptor size, this vector size, by another 1,000 times, but attaining the same predictive accuracy. You learn some kind of propagation operator I will show you later on. Okay? So this is the power you can get by using this learning approach for this graph algorithm. The second problem I mentioned to you is related to more like a complex network. So where you have this particular case is just a bipartite graph. One side is people, the other side is shops or item. And people purchasing different items at different point in time, right? You might have different time and also maybe some context information here. And the goal is to take this historical network and learn some kind of representation for each individual person, each individual item. Hopefully, this learned representation is able to capture the historical information about the preference of the user and then the property of the item, such that you can make a prediction what kind of people will like what kind of product, and more extremely, you want to know when he is going to need that particular item. Okay, so one familiar formulation you might encounter before is treat this as a matrix factorization problem. Okay, so suppose the simplest model is going to just ignore the time on this complex network. It's going to I'm just going to look at the connectivity. Okay, if that particular user has ever purchased that item, I'm going to have an entry of 1 in this matrix, otherwise it's 0, okay? It's a sparse matrix. And then in order to obtain some kind of a descriptor for the user and descriptor for the item, I'm going to say that I'm going to approximate this sparse matrix R by the product of two row-rank matrices. So it's a product of U matrix and V matrix. So each row of this U is going to be something like the descriptor or embedding or vector representation for the user. And each column of V is going to correspond to one item. Okay? So you can actually look a little bit more into how do you actually obtain this UV. It's actually an interesting iterative algorithm, shares some similarity with this graph feature extraction algorithm I showed you earlier. Okay? So this is an approximation problem we want to solve. And essentially, the way you obtain this UV is by solving an optimization problem with respect to U and V by minimizing the L2, the square distance between the R matrix and the product of UV. Okay? So the simplest algorithm is called alternate least square minimization. So you will, again, initialize each one of these node item here with some feature vector, yeah, embedding, very similar to the molecule case, right? And similarly, you will also initialize each one of these user as embedding vector UI. So when you try to update the embedding or the vector representation for that particular user here, so you actually ask this neighbor of the user, those items this user has ever purchased, to send in this vector embedding and perform a particular update to it. So the particular update is done by solving this optimization problem. Actually, it's a least square problem. You will get actually closed form expression for this. Essentially, in order to update the user embedding, you will have these neighbors items sending this embedding and do some particular transformation. Similarly, for the update of the item embedding, it's also the same thing. You ask those users, whoever has bought this particular item, passing in the messages and perform the particular update, you get updated item embedding. So you do this for all these items, all these users. Once you finish one sweep of update, you go to the next sweep of update. Okay? So in this particular case, it's also message passing. Yeah, the updated thing is also going to be a vector. It's just that the updating operator is different from the one you've seen in this molecular feature extraction process. So again, you will see later on with this graph embedding approach, you can actually learn some update operator instead of this particular fixed one, and be able to learn some embedding which is much more predictive, giving you some more interesting results, okay? And also it's very flexible in terms of capturing the context, the additional information during particular purchasing, and also use the temporal information much better, okay? So these are two examples, and then the third class of example I would like to explain a little bit more in detail later on is this combinatorial optimization problem in computer science, or maybe in some other area. So very often that, especially in social network or complex network, you need to solve some optimization problem on top of it, okay? So for instance, the simplest problem I'm going to explain in more detail is this inference maximization problem. So it's a little bit like a Twitter spreading, right? You want to determine who should initiate the spreading process, or which sets of people should initiate the spreading process, such that the information can diffuse as fast as possible in the entire network. So a discrete version of this is, or the simplest version of this is the minimum vertex cover problem. So essentially, what this problem is asking us to do is, you want to select as small number of nodes as possible in this network, such that you can make sure that every edge, at least one end, is being selected. Because suppose this guy likes it, right? The particular tweets or products, then all the neighbors will know about it. Then there's no point of selecting the neighbor anymore, right? Okay. So all of this problem is very simple to state. It's actually a pretty hard optimization problem because, for instance, maybe two high degree nodes, yeah, intuitively you want to select it, but they might share lots of common neighbors. So the benefit of selecting this pair of high degree nodes is not that beneficial. Then you have to jump to the other side of the network and choose something better, right? So I'm going to describe actually a simple algorithm previously manually designed, but with a very good approximation guarantee. It's actually a true approximation guarantee algorithm, meaning that if you solve these greedily, according to this procedure, the solution is not going to be, it's going to be at the most 2 times worse than the optimal solution, okay? So this algorithm is going to essentially pick edges. So it's going to score edges based on the degree of the node on the 2 ends of this edge. So you sum together the degree of this end and that end. If that particular edge has high degree, then you're going to select both ends of this edge and remove this edge from the network and all these incident edges, yeah, and work with the remaining graph. So in some sense here, you're counting the number of neighbors, right, for each one of these nodes. So again, you can think about it, it's also a message passing process counting. You're asking those neighbors, they all have a tag of 0 if it's not selected. Sending this center node, this 0, and you count the number of zeros, yeah? So it's again some kind of message passing, very simple one-step message passing. And use that past result, this aggregate result, as a scoring function to design your algorithm, okay? So it turns out that you can actually learn the algorithm to do better than true approximation, okay? So the reason why we can use learning is because actually such problem is not just solved in a single instance. So in many industry problems, this type of optimization problem, combinatorial optimization problem, are solved again and again in a daily basis, maybe hourly basis. So maybe today the graph is slightly different because some friends are sleeping and they're not logging in, right? The graph is different. And maybe there's a new friends introduced, a new node being introduced. So every day the graph is slightly different, but they share some similarity. There's a distribution of problems, related tasks. Somehow you will be able to learn across this task such that you can do better in a new problem instance. So that's why you can use this graph embedding operator to also learn the better one, okay? Doing much better than 2 approximation. So the lower the better. Ideally you want to have 1. Based on this learned graph algorithm, you'll be able to do roughly 1, okay? So let me just summarize these 3 sets of application a little bit, right? So you either it doesn't matter whether it's a graph feature extraction problem or recommendation system problem, or it's indeed trying to come up with some algorithm for solving combinatorial optimization problem. They have some similar structure in terms of the previous algorithm you have seen. It's all based on kind of message passing over the network. So first, this graph algorithm, traditional ones, has to design how do you represent this node, right? So you have some either number representation or vector representation for the node, And then you had to hand design or manually design some operator for passing these messages. Okay? So abstract writing is just like there's operator here, taking the neighboring representation, somehow aggregated version of that, and maybe there's an additional feature, you get updated version. So actually many other algorithms I didn't get to talk about here fall into this framework, including things like PageRank for computing the important score of a web page, and that's used in Google for searching, or message passing in graphical model, where you want to compute the posterior distribution of some random variable by condition on some variables. It's actually also doing this. It's just the particular instantiation of this operator is very different. Okay, it's a typical design beforehand instead of chain with the data. Okay, or compute it based on the fixed computation. So our question is, now you get lots of data, and maybe see many of these problem instances of similar type. The question is, can we learn something better? Okay, can we learn some graph algorithms, especially these propagation operators, such that you can do better? Okay, so that's the question. So then we will actually design a deep learning framework based on the graph to do it. Okay, so you can think about it in the space there. Now there are 3 different big type of deep learning model. 4. Okay, one is fully connected. Okay, there's no structure at all. One is convolutional neural net for images, right? And you have these very repetitive patterns. And you have recurrent neural net for sequences, where you process input one by one in sequence fashion. This is yet another class of deep learning model I'm going to talk about. It's called graph convolutional neural nets, or massive parsing neural net, or structure to vector, things like this. Okay? So the input is going to be the complex graph structure. And each node is going to have, you don't know how many neighbors. It can be 3, it can be 4, right? So it's more irregular in some sense compared to images and text. Okay? So what is the key idea behind this? In some sense, in the earlier introduction of these examples, I already alluded what could be a better way of doing it. Okay? So all these algorithms are propagating some messages with the designed kind of operator. So now we are going to, in the high level, is parameterize that propagation, graph propagation operator. So what is this deep learning architecture? The simplest version is something like this. So again, you're going to, for instance, this is your input graph. Suppose this is just a molecule, right? You're interested in. And each one is node is going to correspond to one of these actants. And the actant itself might have some additional feature like atomic number, right? So X is going to be atomic number, right? So I'm going to represent, again, each one is known as a vector. So mu1 to mu6 in this case. Initially, I can initialize as 0 or some other random vector. Then I'm going to update it according to a parameterized neural net. Okay? Suppose I want to update this this mu1. So again, I'm going to ask the neighbor to send in the messages, right? So I'm going to have all these neighbor, suppose this is mu1. So I'm going to have all these neighbors of mu1 to send in messages, which is from the previous iteration. Yeah? Okay? So this is a simple aggregation, just summation, the simplest. I'm going to talk about extension later on. Okay. Once you have aggregated these messages, I'm going to have a transformation here, which is you can think about as a square matrix. Okay. And then if you have some additional information in that particular node, I'm going to also take another matrix or parameter to transform it, and then sum them together and push it through element-wise nonlinearity. So this is like a rectified linear unit, tangent units, and sigmoid unit, things like this. Okay. So this is the simplest version of neural nets you can design. So W1, W2 is going to be a parameter, and it's going to be shared. The simplest version is going to be shared across all the nodes. Right? So it doesn't matter how many neighbors you have. I will always use the same sets of W1, W2. Okay. So the differences in the number of neighbors is summing out. Right. After summation, it doesn't matter whether it's 10 neighbors or 15 neighbors. It's always giving you a vector. Then you can always apply this transformation. Okay. So essentially, you have this parameterized operator. The parameter is not going to fix it, but they're going to learn later on. So you're going to apply it in each one is node. Once you finish one sweep of application of this propagation operator, you're going to start the second sweep. Okay. After you finish T rounds, you're going to obtain some kind of vector representation for each one is node. Right. okay? So depending on your application, so you could use this vector representation differently, right? So if it is a gigantic social network, you want to make a classification for each individual node, this person is going to like a particular thing or not, or this particular account is a fraudulent or not. So you're going to take this vector representation for individual node and link it to some classification function. For instance, logistic regression or regression, okay? So if you want to make a prediction about a pair of nodes, whether it's, for instance, recommendation setting, they're going to interact or not, you're going to take a pair of these vector representation, define some inner products and the regression model or classification model. If you want to actually make a prediction about a property of entire molecule, so you want to say something about entire graph, so you're going to aggregate all this embedding from the entire graph, summation or some kind of pooling, and then define your classification regression on top of that. In terms of the way you can train these parameters, in here, you can use supervised learning, generative model reinforcement learning. I will show you later on, okay? So this is the key idea, right? So by parameterizing the propagation operator as something like neural nets, you get a more flexible, in some sense, algorithm or model comparing to the previous hand-designed model, right? So you can think about the previous hand-designed model, manually designed the graph propagation operator is working with a fixed representation of the network pre-designed, working with a fixed propagation operator you designed, yeah? So now you're parameterizing it as some function, yeah? And learnable, right? It's a more flexible kind of model, you can think about it. But it's less flexible than just, maybe take your graph and treat your graph as a matrix or as a sequence of nodes and then run through recurrent neural nets, okay? So in terms of learning theory, it's having some nice trade-off between the complexity of the model and flexibility of the model in some sense, okay? Of course, I was talking about very simple message passing operator where every neighbor sends me the message and update. There are other ways you can pass messages, right? So there's something called belief propagation in graphical model setting. You can also borrow those ideas here to redesign your architecture. For instance, in this particular case, I'm going to learn some representation not for the nodes, but for the edges. That's also okay, right? Actually, I'm going to learn some representation for each direction of the edges. So it can be forward and backward. It captures information from one side of the graph and the other side of the graph, things like this, okay? So that's why this embedding representation has ij, two indexes, and also the direction matters. So when you try to compute, for instance, in this case, the embedding update from node 1 to node 2, you're going to ask the neighbor of H1 except H2, okay? You are going to ask H5, H6 to pass in the messages, yeah? And use this operator to update the corresponding outgoing messages. So similarly for all other nodes, you are going to apply the same operator here. The parameter is going to share and learned later on based on the application, okay? Similarly, okay? That's the key thing. So besides these two variants, in terms of the differences in passing messages, there are many ideas from convolution neural net and recurrent neural net actually you can use to make this propagation operator more flexible, more expressive. For instance, in convolution neural net, you know about residue network, where you have a direct shortcut between the input from last layer to the current layer. For instance, you can actually take, instead of UT plus 1 going through such a nonlinear transformation, you can actually also have one turn outside of the nonlinear transformation. You can have a combination of linear, nonlinear transformation, have this gig connection. You can even design, if you are familiar with the LSTM, right, a long short-term memory version of recurrent neural nets, then you can also use all this gating mechanism to make it more flexible for getting particular iteration step, things like this, okay? All these can be used to make it more flexible. Yeah, people have tried various variants of this idea, okay? So this is the key idea, okay? Actually, you are going to parameterize these propagation operator on the graph and let all these different nodes share this parameter, okay? And you're going to learn this parameter afterwards, depending on your application. So that will allow us to have very small parameterization, yet being more flexible and expressive than any of the previous hand-designed algorithm, okay? So let's just look at this application I mentioned earlier and see how it performs in practice. So this data set is from Harvard Clean Energy project. They have done simulation over many years and to to compute DFT calculation, and then in the end, they can calculate property like this, power conversion efficiency. So the relative kind of alphabet is number of different type of actants. It's carbon, nitrogen, and then maybe some sulfur, and all these different type of actants. Average number node is this, and average number of edges is this. You really need to go to level 6. If you hand design features, you really need to go to 6 hops to compute these substructures and use that of feature. You will get a feature dimension 1.3 billion, and you can get very small NAE. It's 0.09, right? Considering the range is this, okay? Consider range is between 0 and 12. The MAE in the percentage prediction is going to be this, pretty good, right? So if you reduce it to level 3, like 1.6 million, then you are dropped by 5%. Yeah. So you can use this graph embedding idea, right? But here you want to make a prediction for the entire molecule. That's why once you finish this embedding propagation, you get this vector. You aggregate all these embedding from a single molecule, and then link it to a regression function. This is the additional parameter V you have here for the regression. Remember that in order to compute this embedding, you also have parameter W1, W2 hidden inside this. Okay, you will try to learn V and W jointly, using some regression kind of objective function. So this is what you will see in the normal regression. So this is the label you will try to predict, and you have regression function parameter and also the parameter in this graph embedding algorithm in there. You're jointly trying to minimize this. Okay, the forward again is going to be some forward computation along the graph. In the backward is done by TensorFlow or PyTorch. It's nice. Okay. So you can learn this graph algorithm. So this is essentially the result. So you can look at the number of parameters versus the predictive accuracy in terms of MAE. So this is log scale. So using this level 6 Westphalia lemon feature, you actually have 1.3 billion, right, features. You get this MAE of 0.05. So you can compress it using these hash functions. By 10 times, 10 times. The more you compress, the more you lose in terms of performance. But this learned graph embedding operator is able to come out with very compact representation for the entire molecule. And being able to achieve state of art is like 1,000 times smaller than this, okay? 10,000 times smaller than the original one without any compression, okay? So these two different versions of propagation somehow achieve similar result, yeah? So this is the power you can get by learning the propagation operator instead of pre-design the dimension or the feature dimension. Yeah. So the question is whether it's a fully connected network. You mean comparing to a fully connected network?
Yeah, the graph propagation for the update.
In some sense, after you finish the pooling, it's a fully connected network. But the key thing is you're not going to look at all the neighbors when you're updating the embedding. You're looking at the immediate neighbors or some local neighbors in terms of updating the graph embedding. Hopefully by the propagation process, longer range information comes in, gradually, right? So there you in some sense balance a little bit of how much you get a long range information and how much you spend in computation, okay? Yeah. So of course, molecule is one communication. You can also apply it to Alibaba problem. Right? They have this fraudulent account detection problem. Of course, they also have a recommendation problem. So in this case, the network you have is something like each one is going to be a account. It's called the Alipay account, and actually they have this graph connecting the account to the device ID. So every time you have this account logging into some iPhone, you will connect. Yeah. So it can have node like this and node like this. So a particular account may log in more than one devices, and one device can have many accounts. Okay, so some of these account has been verified, which is bad. Maybe someone reported it, or has been active for long time, or has done something wrong to the system. It has already labels, and then these label points will be used as to set out your loss function, and the graph propagation operator itself can be used with and without the label, right? First, you just have this parameterized operator computing is updated embedding on the network. Only in the end you connect it to this label. So, and the loss function is set up by this. But once it's done, chained, you can use it for prediction for all these accounts. Yeah, okay? So it has been doing much better than any of the previous hand-designed graph feature extraction algorithm. So a particular difficulty in previous approaches, each one of these accounts actually has its own activity information, because this account log in, log out, right? And purchases that. And then there's lots of activity information you want to aggregate together with these network information, because network tells you that the things connected to each other tend to have the same property. Maybe this is a bad guy, right? Because he uses the same iPhone. Yeah, maybe this group of bad people uses the same iPhone to conduct some crime, right? So, but you also want to aggregate this activity information, which is not easy for previous hand design approach. But now by learning, so this is like the XI feature attached to the node, right? So you can easily aggregate it into this propagation operator learning, okay? So we have also tried other kind of applications. This is a cybersecurity problem. I did it with Dong Song from UC Berkeley for actually detecting the malware by representing graph as some kind of a program as some kind of graph structure. So essentially, you know, nowadays it's going to be IoT is hot, and it's projected that in 2020 it's going to be 50 billion of these IoT devices, more than human. Okay, and then they are all connected. And if you somehow affected this operating system, the code, so all these IoT systems is going to be compromised. So there's also the problem: how do you actually detect these malicious kind of programs? Because all these IoT devices, they can be different. And even the same piece of code, when it is compiling down to these different devices, it might have slightly different graph representation. So, but they also have a similarity for the good ones, similarity for the bad ones. So you want to, based on the graph somehow, to search against these malware database. Yeah, each one of these malware is going to be a graph. You want to learn the similarity between them. So you can also use this learned graph propagation operator to be able to do it more accurately. Okay. So, but the nature of the problem is similar. So let me just go to this second class of problem where the nature of the problem is slightly different. So in this case, you have this temporal information, right? You want to take into account temporal information, especially in this case, between a pair of nodes, there may be multiple edges, right? So in the previous case, it's like a single edge and static. Now it's a multiple edge and it's dynamic, okay? How do you actually frame this problem into this graph of propagation operator learning kind of framework? That's a key question. So the way we do it is we are going to have this process called unrolling this dynamic graph, okay, by introducing some additional node, and then you're able to feed this into the previous framework. So how are we going to do it? So we are going to actually extend this graph with the additional axis of time. Suppose we have just three objects here, two persons, David, Sophie, and the book, right? So at the particular point in time, you know, David purchased that book, right? So I'm going to actually introduce this intermediate node, David here, and intermediate node book here, and have this vertical connection, cross connection, okay? So allowing information to pass from the past to the future, right? And then this cross connection to allow information potentially they can influence each other, okay? The next time when Sophie also purchased this particular product, then it's going to be, you know, introduce additional node here, Sophie node cross connection, vertical connection. Yeah, and then by doing this, you're allowing for multi edges, right? So even you have another edge between David and the book, so you can just introduce this David node in future point, and also this book node, you also have this, okay? You're creating this network which allows for this user to evolve, yeah, item to evolve, and also allow the user somehow to connect with other users through this hidden path here, although they have never interacted with each other, okay? So once you have this graph, essentially you will do message passing on this graph instead. So previously, if you are familiar with dynamic-based network for modeling dynamical system, so this is like a deep learning version of the dynamic-based network, okay? So you care about the future, right? You care about predicting the future mostly. So that's why what you will do is initially at the older point in time, so this axis is going to correspond to interaction context like a rating, right? And then comments, right? Observation. These are hidden nodes here, those nodes you want to compute the embedding, okay? So initially, for each one is user, you might have raw feature. You can compute the embedding. And then once there's an interaction between the user and the item, you want to update the user profile, right? Because the more the user purchase something, the more you know about the user. The kind of feature defining the product are the users. Yeah, okay. So you want to then somehow to influence each other. So then you will essentially define some operator, graph embedding operator here, which takes the historical embedding of that user and that item here interact with, potentially that feature for that particular interaction, and then update the representation for the user. Similarly, for the item, you also have the update. You can imagine for each one is node, hidden nodes here, you will get some update, okay? Then at any point in time, each one is user is going to have this vector representation. Each one of these items is also going to have vector representation. As the graph evolves, the corresponding user representation will also be updated. The item representation can be also updated. Then you can actually use that to build some predictive model or generative model for future potential interactions. Okay? So for instance, this is a simple model where you actually build a density model for the future interaction time between a particular user and item. Okay? So remember, at any particular point in time, we have the embedding for user and item. We can look at the inner product between this user feature and item feature, and use that to define some kind of rate of interaction. Okay, the likelihood they're going to, this parameter is going to define some kind of the parameter for the relay distribution. So it's like if the alpha is large, I believe that they're going to interact very, very fast in future time. Very likely, very quick in future in time. If alpha is small, then it might take a long time for them to interact. Okay. And then once you have this likelihood, you have your observed sequence of purchase and also purchase and time, then you can maximize the likelihood to feed this parameter inside this graph embedding operator and also this potential additional parameter in the model. Okay? So if you do that, you can find that you will actually obtain a much better recommendation algorithm in terms of predicting which item the user is going to purchase and also the time when the user is going to come in back and purchase the item. I'm not going to go into the detail. This is some kind of online TV viewing kind of data set. So this is in terms of the rank, how accurate you can predict the next item. The lower the better, similarly, the lower the better for the MAE for the prediction time. But I'm going to talk about a more interesting example, how you actually interpret this model prediction, whether it learns something that intuitively makes sense. So this is a different problem called the temporal knowledge graph prediction. So on the surface, it looks very different, but actually it's the same kind of formulation. So in this particular case, you can think about many events are happening between the people, organization, countries. Yeah. For instance, each one is, you can think about each event is a relational information between maybe President United States visit some other country, right? This country has a trade agreement with the other country at a particular point in time. So it's really a graph which evolves over time if you're able to, extract and process this information from the news, right? So this particular data set has curated, like they claim that the 215 years of events for newspaper, and it contains trillions of events. So the hope is by looking into the history, okay, you'll be able to predict the future. You want to predict what potential events is going to happen, right? And approximating what time, okay? So this problem is very similar to the previous one, except that the node here is not a bipartite graph anymore. It's just node country organizations, agile, particular type of relationships, yeah, okay? So indeed, in terms of predictive accuracy, we are doing better, but just let's look at some of these accurate prediction and see whether it's learning something that intuitive, okay? So this is one example. This is one example. The actual event you want to predict is this, in 2015, somehow there's some conflict between Cairo people and Croatia. At that time, there's a lot of revolution there. And then what is conditioned on the network before that, right? Or the event before that. And then you make a prediction based on our model, it's predicting very accurately the type of events and also the time, okay? So when you look at this graph, or the event happened before that particular prediction target, You will find that earlier in time in May, then there's some negative events. Red is negative events between Cairo and Manchester. Yeah, threatened these people, and then or tourists. And then these tourists provide some aid in May to this group of people. Yeah, here. And then similarly, there's a negative and positive relation happened in the past. So these two paths is like an enemy's friend, right? Enemy's friend enforces the possibility that these two guys will become enemy. Okay, and then the time is also pretty accurate because you have this chain together time, these two time chain together enforces this is going to happen very soon. So this is another example, more complicated relationship. In this case, the COOP is some kind of cooperation, right? And fight or reduce relationship is some kind of trade fight. Okay, so here is Colombia, Ottawa. The actual event happened is this material cooperation. It's also predicted very accurately. The top one is like earlier in time in the history, you had this positive relationship, and then there's also an edge of negative relationship, right? So it's like a friend's friend is a friend, friend's friend, and then if they have common enemy, then it strengthens the tie. Okay, so it looks like this single model learned based on this historical sequence of time is able to capture this type of intuitive reasoning or logic we use for making such a prediction. Of course, the model also learns some other complicated reasoning. Somehow I'm not showing here, or it's harder to interpret here. So in the last slide, I'd like to talk about this application quickly, learning combinatorial optimization. So the key idea you already get, essentially, when we are designing this graph algorithm, we are going to parameterize our propagation operator. And that those parameter is going to be learned instead of pre-designed. So let's just come back to this problem in advertisement, minimum vertex cover problem. And this two approximation algorithm is very simple, nice. You just compute the total degree of an edge, and you select this edge to, once you select it, you remove it, you work with the remaining graph. Hand designed, and potentially not the best, okay? Given that you know that you're solving this problem again and again every day. You want to learn a better one. So you can imagine that I can just frame this problem as a Markov decision process, because I'm going to take this input graph and work on it in a sequential fashion every time I pick some node according to some scoring function. And then the hope is if my scoring function is intelligent enough, then I can just solve the problem with a small number of steps. You want to reduce the number of steps, right? So the mathematical formulation of this problem is some optimization problem like this. So you attach to each one is node a variable, binary, either 0 or 1. You want to minimize the summation of these type of binary variable. If it's 1, it's selected. 0 is not selected. So the constraint is that you want to make sure for every ij pair which has an edge connected. So the variable at 2n, x and xj, is larger or equal to 1. At least one n is selected. Okay? So it's optimization like this with these constraints. And what you do with that previous greedy algorithm is something like this, right? Compute the total degree and then select the end with this. So if you frame this into the kind of reinforcement on your Markov decision process type of framework, so it's the reward is -1 every time you pick a node, yeah? Or you pick a pair edge and reward is -2, okay? You penalize that, okay? You want to maximize the reward. In this case, you want to minimize the negative reward, okay? So the states of this Markov decision process is going to be the current graph and the current selected set of nodes. Right. Okay? And then you have some scoring function. You can think about the action value function. The greedy approach essentially has a very bad action value function. It scores the action without looking into longer term horizon. Okay? It's too myopic. Okay? And then you're going to use this action value function to compute some greedy action, right? The action here is picking the node, yeah. And then once you pick that, you update the states and you start the next iteration here, okay. So what I'm going to do is essentially it now becomes hopefully natural to you. Is going to use this graph propagation operator, parameterized one, to define my action value function to score how good is this individual node. Okay, so I'm going to have a problem input instance. I'm going to run graph embedding operator on top of it. I'm going to get a vector representation for each one of this node. So it's produced by a parameterized operator, remember? And then I'm going to define this scoring function comparing individual node I'm going to pick with the remaining graph, okay? So it's remaining graph is going to be aggregate representation, okay? So this is going to be your action value function, yeah, so it is specific forms like this, okay? And this Q function, you somehow want to learn something which is able to take into account longer term benefit. So you can actually use something that in some sense is standard in machine learning called Q learning, okay? Or DQN, yeah, if you know about it. People use the similar type of kind of formulation to learn the policy of the soft goal, yeah, beating human, okay? So you need to have many problem instances to train it, okay? It's like you have a family, or you have a distribution of random graph, you have a distribution of scale-free graph. And then you use many of this to train these parameters in this action value function. Also the parameter, of course, in this graph propagation operator as well. Once you have learned these parameters in the graph propagation operator, so describing this node and also this, then giving you a new graph, you can just apply this policy, this greedy policy on the graph, and then telling you how to pick the nodes, okay? Yeah, this is the idea. And essentially, let's look at the result, okay? This is some nice visualization. So I'm going to compare three graphs, okay? This is done by this graph embedding operator learning algorithm. This is going to be an algorithm which is picking node greedily, okay? So I'm going to pick high degree node first. Once I pick, I remove those incident edges, work with the remaining. So edge greedy is going to pick an edge based on the degree of the two end. And the three graphs are the same, exactly the same, just because the visualization somehow looks slightly different. So every time I pick a node and remove the corresponding edge, I'm going to advance one frame. Right? I'm going to produce a video of it. So whatever algorithm runs faster and solve the problem faster, it's going to clear up the graph faster. Okay, okay. And then you can look at this animation of it. And so initially it looks like this greedy one, this one is pretty good, right? It's becoming very clear. This is cluttered. It's almost done, yeah. And this one is still quite a lot. But magically, in the end, this one is faster, okay? The larger the graph, actually, the difference is larger. Why is this happening? So because all this greedy approach for doing, let's just look at it again. So it's so myopic. It's not looking at a longer term benefit. And actually, when this algorithm operates, near the end of this algorithm, it's breaking the graph into small components already. They're disconnected. You are forced to, in the end, pick at least one node in each component to cover the graph, okay? So the nice thing about these learned algorithms is it's able to actually take into account the connectivity of the graph into account as well. It learns to take into account the connectivity of the graph. When it's picking the nodes, it picks some nodes with relative high degree, but also make sure somehow the graph is connected, okay? So then near the end, you still have the potential to pick one node and remove large part of the edges, okay? That's the benefit of, parameterizing this graph propagation operator to capture some graph statistics. And also use this reinforcement learning to learn something, considering the long-term benefit, okay? So that's the power you can get by using learning, okay? Learning and graph algorithms. So actually, a similar idea can be used in many other areas. People are talking about learning to learn and learning to optimize even the continuous function, things like learning to factorize matrix, learning for image reconstruction and sparse coding. So it all has this similar flavor. Okay? You are parameterizing the algorithm and learn it with the problem instances. But in this particular case, it's specific to graph algorithms, okay? So these are some quantitative results. So for combinatorial optimization or integer programming, actually there's already some standard, quite efficient solver out there, CICS, industry standard kind of solver. So this CICS is going to essentially, take this problem instance and then using branch and bound, spit out the feasible result one by one. And if you let this CICS run for a longer time, it will produce higher and higher quality solution. So I'm actually using 100 problems. That's why you see cloud of points, okay? Each problem is going to correspond with one dot here. And the different colors for different method. So you can look at runtime versus the approximation ratio. So CICS has this property. The longer you let it run, the better solution is going to give you, right? So when CICS spit out the third solution, it takes like this amount of time, okay? This class of points. So this learning algorithm is actually going to run better than CICS for the third solution of the CICS, okay? And produce roughly about the same, like 10 times faster, but producing about the same solution. If you let CICS run for less time, it can be faster, but the quality of solution is much worse, okay? So people have tried INN approach is again much worse in terms of approximation solution. Of course, it's faster, and then there's two approximation plus faster, but the solution quality is worse. So it has some benefit in terms of learning. You learn the better solution in shorter time comparing to these solvers, which eventually is going to give you the real global optima. Okay. Okay. Of course, the other application I just quickly skip is about adversarial attack to the network. You can manipulate the network in the sense that make whatever classification algorithm based on the graph misclassify something. So again, it's some kind of combinatorial attack kind of problem. You can use simulator to do it. Okay. So we also have, let me just briefly mention about this large-scale implementation. So imagine that you have a graph with 1 billion nodes, maybe 200 billion edges. How are we going to do it efficiently, right? So you need to run this message passing on such a large-scale problem, and also all these nonlinear transformation, and you also have gradient propagation on top of this. Of course, for forward computation, you can use matrix operation, sparse matrix corresponding to the graph, and embedding for each node here. Each iteration along the graph is going to correspond to sparse and dense vector multiplication and feature times this parameter, okay? And element-wise nonlinearity, and you do it multiple times. So another thing that can be done in this case, but typically not done maybe in the numerical linear algebra setting, is you can do stochastic chaining for it. So you can actually sample some subgraph from your bigger network, and then just use that to compute the gradient and update your parameter. So these two together and some additional engineering kind of solution like parameter server architecture, you will be able to scale it to billions of nodes. Yeah. So this is what we did in the company, where you can actually help them to do fraud detection in huge scale networks. So in the end, I'd like to just conclude. So essentially, the key idea or take-home message is very simple. So you're going to essentially parameterize the graph propagation operator. So previously hand designed. Now you're going to learn some vector representation for each node of the graph, but the propagation operator or the update operator for these nodes is going to be learned, parameterized and learned with the downstream applications. Okay, and then this graph propagation operator, the simplest form is going to be a template applied to each one is node in the graph. Yeah. And then that's why you can use a very small compare representation, parameterization, and learn some complex and very informative embedding or representation for the graph. And you can use it for classification, fraud detection, likelihood generative model, and reinforcement learning, learning some long-term policy. If you're interested in more papers, yeah, you can find it on my website. And Nick should have the slides. Okay, that's pretty much of it. Yeah, any question about this? Yeah.
Thank you.
Can you go back to page 26?
26. This one or last?
26.
This one.
So what kind of node feature did you use for user name items?
Right. So node feature can be, user register in your profile can have some rough feature, right? Maybe he has picked some preferences or something like this. It's just, yeah, some attributes, some raw feature. Item has an attribute. For instance, this is some kind of educational related stuff, and then maybe a long description about the author and then the content of this. Yeah.
Do you think it is okay to use, for example, if there is no much low feature we can use in some data set, right? Do you think it's okay we can use some, for example, we can use graph embedding algorithm to get some feature embedding of user and items, right, on my graph. Then, do you think it's okay we use this kind of embedding feature that a low feature, then use graph neural network to refine these low features?
it's possible. You can use whatever approach to come up with the initial feature, and then use this parameterized propagation operator to refine it. In some sense, the molecular design case, the node feature is very simple, almost no node feature, just atomic number, right? So the feature are completely determined in some sense by the topology, the connectivity. And you can think about if you compare this graph propagation operator, learned one, with this hand-designed Weisfelder lemon kernel. That one is completely trying to design and capture the topological feature. So here, you're also trying to capture this topological substructure. But you can think about this learned operator is also, aggregate neighbor combinatorial information and compress it, okay? But the compression process or the hashing process is learned, yeah, okay.
Yeah, because when we do some graph embedding algorithm, like structure to vector network, deep work network, we can get some original embedding features based on, actually, deep work network vector line are based on network structure, right? Then we can get some original embedding features, right? Then, if I don't have attribute feature of user item, then can I use like the...
What's the question?
Yeah.
So the question is...
okay to use the embedding feature trained by some network embedding algorithm as a low feature, then use this kind of low feature to use graph neural network to refine this kind of low feature.
Okay, so the question is essentially there are some existing graph embedding algorithm running in very different mode as this one. So he's saying that whether we can use those existing other algorithms as coming up with some feature representation and use that as initialization for this one. So actually, it's nice that you mentioned about these other approach like node to vector or deep walk. So actually, my recommendation is don't use those. Yeah. So why? Because these previous approach based on node to vector, deep walk, what they will do is you take your graph, first ignoring maybe potential all these attributes in the node, and you first do a random walk over the graph. Okay. You have to design a random walk over the graph. So the random walk you have to design some reset probability or all this probability, okay? Once you finish random walk, you get this trajectory as a sequence. You use some kind of sequence approach to compute embedding. And there are several problems with this. First, you are not able to take into account all these node features simultaneously. The second thing is it is not the inductive approach. It's not generalizable to a new graph, the embedding you learn. So you can think about this graph embedding. And the third thing about the approach is learning in an unsupervised fashion. It's hard to take into account the target information, the thing you want to predict into account. So this approach in some sense is capturing topological information. That's what you need from the graph. It's very easy to incorporate additional node feature or edge feature in the propagation process, which is also not easy for designing separate random walk which take into account those features. The third thing is train the end-to-end by supervised learning. In practice, we always find it doing better.
Yeah, I understand.
Thank you very much. Is there any other question before we close? Because we're...
Yeah.
So what's the core difference between your work and the message pressing, neural message pressing framework?
So it's actually very similar. So you will see that there's a sequence of work related to this. So it's just people is not aware of each other's work. Yeah. So we all have these structured to vect in 2016, but we are doing it more for the molecular property prediction. Later on, there are also paper on something called the neural message passing network. It's essentially the same. Yeah, just the same thing disguised in different form. And once you discover that, you find that they're all related. Yeah. Okay. Now people know that they're all related.
It's way past my bedtime, so we're going to thank our speaker again.
Thank you.